Most enterprise Java developers interact with the Spring Inversion of Control container through a handful of stereotype annotations. You mark a class as a service, auto-wire a field, and rely on the framework to wire the system together. But treating this container as a black box creates significant risks. High-level syntax offers no defense when microservices fail to boot due to untriageable proxy errors or cyclic dependency deadlocks. To maintain stable production environments, we have to look past the annotations and map the explicit memory registries, compilation phases, and multi-tier cache lookups that govern the container at runtime. Today, we are opening up the engine bay to examine container initialization mechanics, the 8-step Bean lifecycle, and the internal 3-level cache architecture. At the scale of enterprise microservices, these concrete mechanics provide the necessary visibility to debug failed initializations and manage complex object topologies. While the basic BeanFactory interface handles standard lazy instantiation and configuration parsing, the enterprise-grade application context serves as a broader execution framework. It integrates specialized services like localized messaging and decoupled event publication loops. This architecture changes how we define a singleton. The classical Gang of 4 design pattern strictly limits object creation to one unique instance per JVM class loader by enforcing a private constructor and a static instance field. Spring, however, locks uniqueness to the specific IoC container context session. This allows you to use standard public constructors. The container enforces uniqueness programmatically inside the DefaultSingletonBeanRegistry, which tracks bean names and instances within an active concurrent cache loop. By moving uniqueness control into the registry, the framework ensures structural integrity regardless of the underlying class access modifiers. Before the container builds an application, it must first establish the structural rules. This is phase 1, bootstrapping configuration metadata. This entire phase occurs before the framework instantiates a single object on the Java heap. The container scans your class path for stereotypes like @service and analyzes these stereotypes to build a bean definition matrix. This metadata map records the target class type, dependency requirements, and lifecycle hooks. Once these blueprints are compiled, Spring calls all registered BeanFactoryPostProcessor engines. This gives the framework a window to alter the architectural blueprints before any instances exist. The property source's placeholder configurer uses this hook to scan your blueprints for placeholder keys, like DB password, and replace them with live system environment variables. This pre-compilation ensures that the container has a complete, validated map of the application architecture before memory is allocated. After the blueprints are finalized, the container enters phase 2, active bean instantiation. Here, the metadata is processed through an 8-step refinement pipeline. Step 1 is instantiation. The container uses reflection or CGLIB bytecode generation to allocate a raw heap memory snapshot for the object. In Step 2, Spring populates properties. It identifies dependencies, looks up their references in the singleton cache, and injects them into the fields. Step 3 checks the aware markers, injecting infrastructure details like the context string ID or a reference to the parent factory. Step 4 passes the raw object into the post-process before initialization method of any active Bean post-processor interceptors. This leads to Step 5, the initialization setup sequence. Methods annotated with post-construct fire first, followed by the after-property set logic, and finally any custom init methods. Step 6 is the post-initialization phase. This is the exact technical location where Spring spins a proxy wrapper around your raw object. This proxy, either a CGLIB subclass or a JDK dynamic proxy, is the mechanism that enables cross-cutting features like @transactional or @async. Step 7 publishes the completed bean to the concurrent cache registry. The bean remains here until Step 8, the destruction hooks lifecycle, which triggers during a graceful application shutdown. This sequence ensures that every Spring bean is not just a standard Java object, but a fully prepared unit of infrastructure. But this pipeline faces a challenge when the object topology introduces a circular loop, where bean A requires bean B, while bean B simultaneously requires bean A. If you use constructor injection, this loop creates a hard blockade. Because the container must evaluate parameters before instantiation, no pointer address or heap reference exists for the incomplete constructor. This absence of a reference triggers a fatal bean currently in creation exception loop that halts the application. While constructor-based circular loops require an architectural redesign, Spring includes a built-in mitigation for loops involving setter or field injections. To untangle these loops, the DefaultSingletonBeanRegistry employs a structured three-level cache architecture. The first level cache is singleton objects. This concurrent hash map stores fully initialized, production-ready singleton instances. The second level cache is early singleton objects. It stores raw instances that have executed their constructors, but have not yet undergone dependency injection or proxy wrapping. The third level cache is singleton factories. It holds lightweight object factory lambda references. These factories wrap the raw object immediately after memory allocation, allowing the container to perform early AOP proxy checks if a circular reference is detected. By segmenting Bean states across these three tiers, the framework can pause and resolve dependencies between partially constructed objects. To see this in action, imagine Bean A is initiated via field injection. Spring executes the constructor and places an object factory lambda reference for Bean A into the third level cache. Spring notes a requirement for Bean B, pauses A's thread, and begins instantiating Bean B, dropping B's factory lambda into level 3 as well. When Bean B ascends to populate its fields, it finds the requirement for Bean A and triggers a sequential lookup across the cache matrix. The lookup misses level 1 and level 2, then hits level 3. The engine extracts Bean A's factory lambda to pull an early reference. Spring records this early reference inside the second level cache and removes the factory pointer from level 3. Bean B safely injects this early reference of A, completes its own post-processing, and is promoted to the first level cache. Control returns to Bean A's thread. It finds the completed Bean B in level 1, injects it, and completes its own lifecycle steps. The circular loop closes without a runtime failure. This promotion cascade ensures reference safety, even in complex, interconnected object topologies. Dependency injection is a deterministic execution pipeline. The process coordinates metadata compilation, reflective instantiation, and sequential lifecycle hooks to manage object state across the cache architecture. Defining the boundaries of these internal registries enables the resolution of complex circular dependencies and proxy-related failures that annotations alone cannot solve. Master the lifecycles, understand the caches, and stay under the hood. Thanks for tuning in to Finite Bytes. Hit that subscribe button and we'll see you in the next episode.